Welcome to Chapter 5, Thermodynamics, where we will be studying heat, really the study of energy and its transformations, which is known as thermodynamics. And specifically, we will also be focusing on chemical reactions and energy changes involved in chemical reactions. So you should have gotten some definitions. So let's just kind of review the definitions that you're to get from your textbook. First of all, just a basic definition of energy: capacity to do work or produce heat. There are two different types of energy that we'll be looking at: potential energy or kinetic energy. And if you've already had physics, then these should be pretty familiar. The equation for kinetic energy we will come back to and use a lot more when we study gas laws. Other definitions that you should have acquired are about the laws of conservation of energy and the laws of the first law of thermodynamics. They're pretty similar. They kind of go hand in hand. That energy is neither created nor destroyed, but can be converted between forms. So therefore, all the energy in the universe is constant. It is conserved. If you have any questions on these definitions, pause this podcast. Go back, take a look at what you've written, and if you need to fix something, then go ahead and do that. Alright, some new information. State functions. When we talk about a state function, we're looking at about a property of a system that depends only on the current state of the system, not how it acquires that state. And so, for instance, energy is a state function. The example we use: if we throw Mr. Cassidy back up on the top of Mount Everest, whether we dropped him there by a plane or by his hiking, he still has the same amount of potential energy. And there's lots of examples of things that are state functions and things that are not state functions. So while energy is a state function, work is not a state function. Why is work not a state function? Well, if you remember from physics, work equals force times distance. So when you change the distance, you change the amount of work. And the idea behind a state function is the path that you take there, does it matter about the end result? When we're looking at energy and chemical reactions and the heat evolved, most of the time we don't really care how the little baby steps are to produce that heat. We just care about the total overall. Was heat released or was heat absorbed? So relating these two things together, the idea of energy and work and heat, we use a quantity called delta E, the change of internal energy of the system. Q, the symbol Q, refers to the heat flowing into or out of the system. And one of the things with thermodynamics that you really need to pay attention to are sign conventions. If your quantity is positive or negative, what does that mean? So if we've got a negative Q, your energy is leaving the system to the surroundings. Positive, it's going the other direction, entering from the surroundings into the system. W is work, done by or on the system. And same sort of thing, we got to take a look at our sign conventions. If work is done by the system, or if work is done on the system by the surroundings. If the whole phraseology of on the systems and the surroundings is kind of confusing to you, most of the time what we're concerned with in chemistry is the system. What is the chemical reaction inside the beaker or inside our container? Surroundings, that's really not usually what we're taking the temperature of, but to keep with the first law of thermodynamics, where does the energy come from? It would normally come from the surroundings. So we're kind of focusing on what is the flow of energy from system to surroundings. A little more about this work idea. Commonly, the only kind of work produced by chemical or physical changes open to the atmosphere is mechanical work associated with change of volume of the system. So when we move into gases and we start changing things like pressure and volume, we're going to see that there is going to be a change in temperature. So how does that relate to pressure? And again, this is kind of a physics thing, but how do you relate pressure and volume and work together? We have the expansion of a gas, for instance. If we increase our volume of a gas, we will see that we end up with a negative work, that the energy of the system is actually decreasing. Try to move that out of the way. Work has been done by the system on the surroundings. And by contrast, if we compress a gas, in other words, we're decreasing our volume, what does that do to the amount of energy? We're going to see work being done on the system by the surroundings. So kind of relating the idea of energy, keeping in mind that energy, most of the time we're talking about heat when we're focusing with energy in chemical reactions. But we could also have discussions just within a single state, not even a chemical reaction, but if we change pressure, what does that do to our amount of work? Two terms that we covered last year, endothermic and exothermic. Since we are going to be looking at chemical processes with each chemical reaction, or even with a phase change, we'll be trying to figure out whether a process is endothermic or exothermic. If it is endothermic, energy is flowing into the system. So your temperature, we end up with a couple different things. First thing I want to point out to you is when we start to calculate this quantity, delta H, please note, delta H is going to have a positive sign. What this little graph is called, and you'll see these in your books, these are called enthalpy diagrams. And they kind of help us see what the flow of heat is from beginning to end. So when we have our reactants and we are putting in heat to a system, what happens to it? So what might we see temperature-wise? That's something we're going to kind of look at with labs and so forth. By contrast, if heat is being released, if a system is exothermic, then we will see a negative delta H, and we'll talk about what delta H means in a second. But again, with this enthalpy diagram, you can kind of see what is the energy that a reaction started with, what is the energy that a reaction ended with, and if it's a difference, a negative difference, we say that is an exothermic reaction. So what is this delta H thing? Well, delta H is the symbol that we use to talk about enthalpy. And enthalpy is our really fancy word to basically mean heat. Through the course of this year, we'll look at many different ways to calculate delta H. We're going to cover 3 of them in this unit, and then one we'll get to a little bit later on. So the first way that we can calculate delta H is by using a technique called a calorimetry. Now we have done calorimetry in previous experiments. If you remember burning of a Cheeto or a Cheez-It or something like that with a little cup of water or a can of water overhead, that was a calorimetry experiment. And then we have what is known as Hess's law. And there are 2 versions that we're going to look at with this unit. Hess's law. Okay. And the 4th way we will be investigating in another unit when we start talking about bonding and so forth, but we will be calculating bond energies, how much energy is found within a chemical bond, an ionic bond, covalent bond, and the like. Okay, so let's talk about calorimetry just a little bit. Amount of heat absorbed or released during a physical or chemical change, we're going to be measuring that using change in temperature with a known quantity of water in something known as a calorimeter. And so this is called a bomb calorimeter. We don't have one, but if you are a food chemist or a food scientist, you would have these at your disposal. And if you take a look in your textbook, it'll have a lot more information about how the bomb calorimeter works. But basically, as you kind of see, you have some sort of sample in here, and you are monitoring the temperature change of the water outside of the sample. So the idea is that heat being released by one substance is going to be absorbed by the other substance, and we can use the combination of those 2 things to figure out how many calories or how many joules are found within that particular substance. More commonly, the type of calorimeter that we use is called the coffee cup calorimeter, where we've got a series of nesting styrofoam cups for a little bit of installation, stirring the solution with our stir rod, and then monitoring the thermometer with the thermometer the temperature change. So this could be a chemical reaction, or it could be a phase change, looking at how much heat is involved with going from solid to liquid or liquid to gas. We can use calorimetry for both of those things. The equation that we use for calorimetry should look familiar. Q equals M, which is mass, and the unit that we use for mass is in grams. Delta T, this is our change in temperature, and this can either be in degrees Celsius or in Kelvin, either one. And then S is the symbol that your book uses. A lot of other books also use C, so you may remember from a little video that we watched last year, MC, delta T. This stands for specific heat. And I have a feeling that I already, yeah, there we go, specific heat capacity. So Q is going to be our lost heat that is either lost or gained by the particular, by the particular substance. Like I said, M is your mass of the substance. And then our temperature change. We need to talk a little bit about units. The units of Q is J, joules, which is going to be important because there are other units that do not use joules, they use kilojoules. Specific heat is going to be joules per gram degrees Celsius, or you will also see this joules per gram degrees Kelvin. They're going to be exactly the same number, because if you think about what is the change in temperature, it shouldn't matter if your temperature is in Kelvin or in Celsius. So you'll be presented with problems that are both in Kelvin and in Celsius, but just know that it doesn't really matter. The specific heat is going to be the same. You don't have to do any sort of conversions with your specific heat calculation. Specific heat substances, or specific heats for all kinds of different substances, are known. It is the amount of energy it takes to raise 1 gram of a pure substance by 1 degree Celsius, and you have that definition in your notes packet. The lower the specific heat, the higher the temperature change when it's heated. So if it's got a low specific heat, that means it's going to be readily giving off its heat. It's not holding on to it. You're going to feel it. So metal tends to feel a lot hotter because it tends to have low specific heats. The higher the specific heat, the lower the temperature change when it's heated. Okay, as I said, some units we need to kind of look at. And you may see the idea of a Newton meter in various other classes, or maybe in physics or something like that. So just to kind of see how these are related, but joules are the SI units for heat. Calories, we use these quite frequently. Do be aware though, and we talked about this a little bit last year, the difference between calorie with a small c and calorie with a big C that you have listed as nutritional information on your food label. Calorie with the big C, there are 1,000 little calories, so it's actually like a kilocalorie instead of a 1-to-1 ratio. And then finally, just kind of, just the relationship between calories and joules. 4.18 joules in 1 calorie. Again, note calorie with a little c. And then sort of trivial pursuit, BTUs. A lot of things in industry are rated by BTUs, so that's how BTUs would fit into this whole picture. We're going to do some examples with calorimetry calculations, and that is in another video.